worse than the other time. I know. And we're running out now. Badly running out. Welcome to a rather pictorial edition of Algebra Workout. Now this one's all about eigenvectors. So what are they? Well, let me show you. I've applied a linear transformation given by this matrix to this photograph of Alan. And this is the result. Now, it seems to be stretched in this direction, and there appears to be some sort of reflection involved. But not everything has changed. There is at least one line that's stayed invariant, although there's been a scaling along that line. But we can explain exactly what's happened by using the ideas of eigenvalues and eigenvectors. The key idea is to find those lines from the centre of the picture here, the origin, which remain unchanged under the mapping. They're the invariant lines, and they're called eigenlines. Now, because a vector can be used to specify a line, that leads you to the idea of an eigenvector. Eigen, by the way, gives away the German history of this branch of mathematics. It simply means special or characteristic. So, you're looking for special vectors, special lines, and special values. Well, at least Alan is.
Yes, and I need to find any special lines using the algebra of transformations, and that means the algebra of matrices. Let's take for granted that there are some lines that remain invariant under some transformation. Francesca has suggested that there is at least one. Let's now consider the general case. If a linear transformation is represented by a matrix A with entries small a, b, c, d, then if you want a vector xy to have its direction unchanged by this linear transformation, what you need is for a times xy to be equal to k, a scalar multiple, times xy. So it'll be in the same direction, but it'll be scaled. So we really want abcd times xy to equal k times xy, where k is that scalar multiple, a real number. The k is called the eigenvalue, the scaling factor in our special direction, and the direction vector xy, if it exists, is called the eigenvector. Now, I'm going to rearrange this matrix equation so that everything is on the left-hand side. So the kxy becomes minus kxy equal to 0, 0, the zero vector. Now, because I know that this will simplify what follows, I'm going to rewrite this as a pair of simultaneous equations. Going along the first row, ax times plus by minus kx equals 0. And that gives us the first simultaneous equation. Ax plus by minus kx equals 0. And going along the second row, we get cx plus dy minus the ky equals 0. And that gives us our second simultaneous equation. Cx plus dy minus ky equals 0. Now, for reasons which you'll see in a second, I'm going to rewrite these two simultaneous equations as a matrix equation. We have here an a minus kx and a by. We have here a cx and a d minus ky. So we can write the matrix equation a minus k, b, c, d minus kxy equals 0, 0. And we have a matrix equation now. Now, you might remember from your work in matrices that to solve an equation such as this, we multiply both sides by the inverse of this matrix. If you do that, it leaves you with xy on the left equals the inverse times 0, 0, which is just 0, 0. And that isn't a very helpful solution, xy equals 0, 0. It's a trivial solution. We don't have any eigenvectors. So the only way we're going to find eigenvectors is if this matrix does not have an inverse. In other words, the determinant of this matrix has to be equal to 0. So if we evaluate the determinant in the usual way, that's a minus k times d minus k minus bc, that has to equal 0. Now, by multiplying out these brackets and rearranging, we get the following quadratic equation. K squared minus a plus d k plus ad minus bc equals 0. And if we can solve that equation, it has a maximum of 2 roots, then we have our eigenvalues. There's a trick about actually remembering this equation. Notice the coefficient of k is a plus d. Well, that's just the sum of the leading diagonal, and we call that the trace of the matrix A. Also, the AD minus BC is our old friend, the determinant of A. So that's quite a helpful way of remembering k squared minus the trace of AK plus the determinant of A equals 0. Now let's go back to our two simultaneous equations. AX plus BY minus KX equals 0 and CX plus DY minus KY equals 0. We call these the eigenvector equations because once we've found K, we can find our eigenvectors from these equations. And the K squared equation, the quadratic equation, is called the characteristic equation for this particular problem. Now when you actually come to find the eigenvectors, it's helpful if the eigenvector equations are slightly rearranged as follows. A minus k times x plus by equals 0 and cx plus d minus ky equals 0. Francesca.
Well, let's find the eigenvalues and eigenvectors of this matrix. A half, 3 halves, 3 halves, a half. And try and see why Alan went that funny shape. OK, I'll start with the characteristic equation. Now I need to work out the determinant of this matrix. Now that is a half times a half minus 3 halves times 3 halves, which is a quarter minus 9 quarters, which equals minus 2. And I need the trace. And that's the sum of the diagonal entries, which is a half plus a half, which equals 1. Now this gives me the characteristic equation, k squared minus 1k minus 2 equals 0. Now that's a quadratic equation, and fortunately it factorizes 2, k minus 2 times k plus 1 equals 0. So the solutions are k equals 2 and k equals negative 1. And those are the eigenvalues of this matrix. So now we know that Alan's been stretched by a factor of 2 in one direction and by a factor of negative 1 in another. But what are these directions? What I'm going to do is take each of these eigenvalues, 2 and negative 1, in turn and substitute them into the eigenvector equations to find the corresponding eigenvectors. I now need to rewrite the eigenvector equations, substituting the values for A, B, C and D, namely a half, 3 halves, 3 halves and a half. So first of all, k equals 2, and I'm just going to use the first of those eigenvector equations. Well, substituting in, that gives me a half minus 2 times x plus 3 halves y equals 0. That is negative 3 halves x plus 3 halves y equals 0, which is negative x plus y equals 0, which means that y equals x. Well, I could have substituted this value of k into the second equation and obtained the same result, which is a good check. So we have an eigenvalue of 2 and an eigenline y equals x. But what does that tell me?
The eigenline is y equals x. That's a 45-degree line up here, and the eigenvalue is 2. But what does all that mean? Well, if I take any vector in this direction along the line y equals x, if we apply the transformation to that vector, then the result is still along y equals x, but twice as long. Let's take another one. Let's look at one going in the negative direction. There's the vector, apply the transformation, twice as long. So if we want to choose an eigenvector, we can choose any vector running along the line y equals x. Here's one. This vector, which is a half, would be perfectly acceptable as an eigenvector. So would one coming in the opposite direction, say negative 1, negative 1, another eigenvector. or a large one along y equals x, like 3, 3. But to be sensible, the easiest one arithmetically to choose is the vector 1, 1.
So that's one eigenvalue eigenvector pair. One special direction on the distorted photograph is the 45-degree diagonal, along which every point originally on the line is still on the line, but twice as far from the origin. But what about that other eigenvalue, k equals -1? Well, let's use that in the first of the eigenvector equations. For this, I'll get a half minus -1 times x plus 3/2 y equals 0. So that is positive 3/2 x plus 3/2 y equals 0, which is just x plus y equals 0. So y equals -x. Now, the eigenvalue, or the stretch factor, is -1, and the eigenline is y equals -x. And that means that if I take any vector from the origin along that line, then the result of applying the transformation will be to multiply the vector by a factor of -1. And that doesn't stretch it or shrink it, it flips it onto the other side of the line from the origin. Let's look at that in pictures.
So, any vector along this line is reversed in direction but stays the same size. A vector like this would simply end up like this. Opposite direction, same size. And one originally in this direction would end up like that. So in this case, an eigenvector is any vector along this line. For example, -2, 2. Or perhaps the one that's arithmetically simplest, 1, -1.
So this linear transformation stretches Alan by a factor 2 in the direction y equals x, and by a factor -1 in the direction y equals -x, which has the effect of flipping him over this diagonal line. So the eigenvectors and eigenvalues do explain the effect of that linear transformation. So if we took this point in Alan, say the bottom of his earlobe, and see what happens, the effect of the linear transformation would be the distance parallel to y equals x would be doubled. It looks like it's further away. And the distance parallel to y equals -x would be multiplied by -1. And it looks like he has been flipped over onto the other side.
Well then, suppose you wanted to distort an image in a particular way. Then there's a method of using eigenvectors to construct the matrix you would need to do that. That's why finding eigenvectors has its uses.
Eigenvectors turn up in all sorts of matrix algebra. It's not just a way of describing transformations in pictures. And you're possibly already beginning to sense how fundamental our earlier work on matrices was. Now, we introduced the determinant, for example, as a way of calculating the inverse of a matrix. And here it is, turning up again in the characteristic equation.
Which is just one of the reasons why mathematics is such a rich and fascinating subject.
Oh,
Well,
so
I think
great.
that's been